Okay, so we're going to be starting a bit of a history lesson, going through the fascinating story of a lot of these scientists who contributed to our understanding of the structure of the atom, something that's very difficult to conceptualize, and as technology progressed, we got more and more detailed understanding of what was happening at such a tiny, tiny scale. The story actually begins with a scientist, or a person, I should say, who wasn't a scientist, who's not on your list there because he wasn't a scientist at the time, he was a philosopher. Around 400 BC, there was a philosopher by the name of Democritus in ancient Greek times who was considering matter. And he was considering the idea of whether there was the smallest bit of matter. And something that we actually thought about when we first started our study of electrostatics, we took the idea of an object and we broke it down step by step in like a hierarchy, right? We started from objects and broke it down to molecules, down to atoms, and so on and so forth. And at the time, they didn't have names for these things, but they just were considering, is there some smallest bit of matter, or does it just keep going? And there's some philosophers who thought, yes, it just keeps going, it's just getting smaller and smaller and smaller. And then other philosophers, like Democritus, thought, no, there's got to be some tiniest bit of matter. And so he came up with the idea of the atom. He just gave a name to it. That must be some smallest bit of matter, whatever that is, that's called the atom, because in Greek, the word atom means indivisible. So he figured there's some tiniest bit that you couldn't get any smaller than. It was an indivisible bit of matter. But there was no experiments being done, it's just a concept at the time. So we fast forward thousands of years till about 1803. We get to John Dalton, our first scientist on your packet there. And he was an English chemist, and he was the first one who had the evidence for the existence of atoms. He was doing experiments trying to figure out the ratios of different elements and how they combine to make different compounds. And he kept realizing, kept finding that the elements combined in whole number ratios, meaning that there must be some smallest quantity of that element. So he discovered evidence for the atom. He didn't actually find the atom, there was just evidence that there was some smallest bit of that element. And so when it came time to make a model, here's Dalton's model. I mean, that's it. Right there, that's it. It's just a sphere. Because like a good scientist, he realized that he knew nothing really about the interior of the atom. He knew that atoms themselves were neutral, but he hadn't discovered any positive or negative stuff, and so that's it. This came to be known as the billiard ball model, like billiard balls, pool balls stacked together to form the different compounds. He had no idea if there was a structure inside, so like a good scientist, he didn't think there was any, right? And that's how science is done. That's how good science is done. If you don't have evidence, then you can't just make guesses, and so here's his model. That's it. All right. So we fast forward to 1897, J.J. Thomson, who was using cathode ray tubes. Now, we've actually talked about cathode ray tubes before. We saw a video of a cathode ray tube inside an oscilloscope when we started our study of magnetism. And so here is a model for a cathode ray tube, and when you put a large potential difference across it and you evacuate it from air, there were these green rays inside. It was glowing green. At the time, they had no idea what these things were. In fact, a lot of people weren't even using it for scientific purposes. They were using it for entertainment purposes. Some traveling salesmen would have these cathode ray tubes, and they'd give their show trying to sell their wares, and they'd entertain the kids by putting a potential difference there, and it would glow green, and they'd say, oh, there are spirits inside, and buy my things, they'll help protect you from the spirits. But scientists knew better. They realized there must be something interesting happening here. Here's the picture of the model on your paper. Point C is the cathode. That's where the green rays are emanating from. Okay, so we have these green bits, what look like light shooting across there, and so they wanted to test it out. They wanted to see, is this light? They already knew that light was a wave, and how do we test if something's a wave? Well, the four defining properties. So one of the ways to test is diffraction. So they thought, okay, let's put a little, well, I don't know, obstacle there, like when we did the laser shining on the hair. What should happen is, well, if this is light, it should diffract and form a diffraction pattern on the screen over here, the detector screen. And they found no such pattern occurred, and so since the rays did not diffract, that proved they were not waves. And so if it's not waves, it must be particles. They didn't know why it was glowing, but this must be a stream of little bits of matter going across here. So they figured, okay, let's test the properties of the matter, maybe by putting a potential difference across here. That's where these plates are. So if we charge this one up positive and this one up negative, they found that these cathode rays were deflected this way, right? And so they must be attracted this way. So here's the results. They found that the rays had to have been a stream of particles. They're not waves. Since they're attracted to the positive terminal, they must have a negative charge. And by doing some careful calculations and measurements here, they found that the mass of these particles were actually much smaller than the approximated mass of the atom at the time. And so for the first time, they found there was something smaller than the atom. So these little tiny bits of matter had negative charge. Clearly, Thomson had discovered corpuscles. You all know corpuscles, right? You've heard of those? No? Well, luckily, soon after that, they came up with a different name, electrons. Okay, so Thomson discovered the electron, a tiny bit of matter with a negative charge. There's now something smaller than the atom. Okay, so the time's come to restructure the model. So here was the original model, and Thomson said, okay, I found these tiny little bits of negatively charged particles, but he didn't know where they were, so we just assumed maybe they were all sort of randomly strewn throughout the atom, and he didn't know they were moving, so he didn't show them moving, right? Because again, that's good science. If you don't know something, you can't just guess. But he did know the atom itself was overall neutral, and so if all these negative particles are there, there must be some positive stuff also, but again, being a good scientist, he actually had not discovered any positive particles, so he just figured the rest of the atom is sort of filled up with positive stuff, sort of like smeared all throughout, right? So here's his model. The positive part of the model of the atom is smeared all throughout, and the negative charges are little bits of matter, maybe suspended within the positive stuff. Again, this is good science. He didn't find a positive particle, so he didn't assume there was a positive particle there. This came to be known as the Plum pudding model. This is probably not exactly what you're thinking of. It's not like a bowl full of pudding like we're used to. Thomson was British. In England, pudding is a pastry, right? So here's a picture of plum pudding. It's sort of cakey stuff, and these little bits here are the plums. So the cakey stuff, that provides the structure, that's the positive stuff, sort of filling up the space. And these little bits here, these are the plums, those are the negative electrons that are suspended throughout. So here is the new version of the model here, the Plum pudding model. All right, we're going to backtrack a little bit in time, just because it makes a little more sense when we tell the story. Let's go to Röntgen. So here's a picture of Röntgen. That is a scary dude, right? This is a scary looking guy. He's going to haunt your nightmares. All right, okay, so put it back to normal. So in 1895, Wilhelm Röntgen discovered X-rays. So he was also working with cathode ray tubes, and in his lab, he had all sorts of stuff there, and he was trying to figure out whether these green rays of light, they still thought they were light at the time, could penetrate different materials. So he would cover the cathode ray tube in different materials. So for example, maybe he covered it in like some heavy black paper, and he turned off the lights and turned on the cathode ray tube, and he discovered somewhere else in his lab, photographic plates were being exposed, which means some sort of radiation was somehow coming out and penetrating the paper covering up the cathode ray tube and exposing the photographic plates. He didn't know what these rays were, so he called them X-rays, X being for unknown. Later on, it was discovered that, and Röntgen figured out, that these X-rays are produced when, there's a picture of the first X-ray. Right? He wanted to take a picture, wanted to see whether or not that these X-rays could penetrate human skin. So he was going to put his hand there, but he didn't know if it would hurt or be damaging. So he said, "Honey, come in here." So Mrs. Röntgen came in here, said, "Put your hand over here." So put her hand there, and he left the room. And here's a picture of the first X-ray. That's his wife's hand. This over here is her wedding band. This is the picture of the first X-ray. And she had a very famous quote. She said, "I've seen my own death." Those Röntgens, they're a fun bunch, right? But think about that. For the very first time, people could see their own bones without some horrific accident or some surgery being done, right? So that's kind of freaky. That's what's going on here. All right. So it's discovered, and Röntgen figured out, that this happens when fast-moving electrons suddenly slow down. And, of course, they emit radiation. We know this, right? All electromagnetic radiation is produced when charged objects, charged particles accelerate, speed up, slow down, change direction. So in this case, these electrons are moving fast and they suddenly slow down, they accelerate negatively, they lose their energy as X-rays. Now Röntgen is German, so of course he used a German word to describe this, and the German word is Bremsstrahlung, which literally means breaking radiation. But of course, it's German, right? So it's got to be pronounced Bremsstrahlung, right? Because, it's German, right? It's very harsh language. Pretty much everything said in German sounds angry. I took 2 semesters of German when I was in graduate school. Ausgezeichnet, that actually means outstanding. It's actually a compliment, but it sounds like you're cursing someone out. So Bremsstrahlung, that means breaking radiation. I've always felt if you're going to go to a battle of the bands with a heavy metal themed physics band, I think Bremsstrahlung would be like a really good name that would inspire fear in your opponents. All right, anyway. So again, when we talk about this, these electrons, they slow down, they lose energy. And the assumption when we do problems with this is we assume all of the electron's kinetic energy becomes the energy of the photon given off. Now, this is really not correct. It's not even a good approximation. But when we do problems, that's sort of the guess we make, because it gets more complicated than that. The electrons lose their kinetic energy as the energy of the photon of the X-ray coming out. So let's do a couple problems here. Let's turn our problem set to number 5 and 6. And pause the video, try your hand at these, then come back to see how I solve it. Okay, so number 5, we have these electrons, they're losing energy. We're going to assume all the energy comes out as X-rays. So just like we said, kinetic energy electron is the energy of the photon. We just replace it with the equations 1 FmV squared equals HF. We're going to solve the wavelength. So we replace F with C over lambda, so we have HC over lambda. We're solving for wavelength, so no, it's just algebra at this point. All right. Well, we see HC. Oh, that's nice. There's HC, so we can use our little shortcut of 1240 electron volt nanometers. And we want to get our answer in nanometers anyway, because, pretty much everything else in nanometers, might as well get this one in nanometers to make comparisons. And it's an electron, because there's always an electron here, right? Because that's what it said. And we got the mass of the electron, we got the speed, everything's looking good. Except, of course, for the fact that if we do 1/2 mv squared, this is going to be in joules, right? There's electron volts. We have to do some sort of unit conversion, so no matter if you do it at the top or the bottom, you choose whichever you like. I'm going to do it at the top here. Here's our conversion factor, this many joules per electron volts. Electron volts go away, we're left with joules, cancel the joules in the denominator. And like I said, that's one of the major hurdles in this topic, is just being really careful with your units. If you're not careful with the units, you're going to answer that really don't make any sense. Now, of course, you don't have to use the shortcut if you don't want to. You can use the value of H, that's in joule seconds, but then you have to use the value of C, and then in the end you have to convert to nanometers if you want to make comparisons. So, it's 6 of one, half dozen of the other. We should be getting 0.121 nanometers, or 1.21 times 10 negative 10th meters, but if you put in nanometers, then we can compare it to other wavelengths we've been doing in these problems. All right, number 6 here. I know from experience a lot of students start with this equation, Ke max equals EVS, and if you did that, you're actually wrong. Even if you, in the end, got the right answer, you're thinking about this wrong, because this is an equation dealing with the photoelectric effect. This situation here, that if you shine light on a metal, electrons are ejected, and then we stop the electrons with this stopping potential, but that's not what's happening here, right? So even if you're doing this, you're getting the right answer, you're thinking about it wrong. You got to stop that, right? This is sort of the reverse process. An electron's already moving, and it stops and gives off the X-ray. So here's what's actually happening. You want to picture an electron being accelerated through 300 volts of potential difference. And so it's accelerated towards the positive plane, and it comes shooting out with a large amount of kinetic energy, and then there's a target, and when it hits the target, it all of a sudden loses the kinetic energy, and it comes out as an X-ray photon. So it's almost the exact reverse of the photoelectric effect. So we start with this again, this assumption that Ke electron equals E photon, which is equal to HF, and we're just trying to solve for the frequency, so frequency equals kinetic energy electron over H. Now, how do we get the kinetic energy electron? Well, it's conservation of energy, right? It gained kinetic energy by being accelerated through a potential difference of 300 volts. So let's be smart about this, right? If it went through a potential difference of 300 volts, it must have gained, how much? 300 electron volts, of course, right? That's the usefulness of using the electron volt. That's why we like to use it. All right, then H, well, now again, it's a matter of using the right units. Are we using the 6.63 version or the 4.14 version? You got to line up your units. We should be using the 4.14 version because this is an electron volts, that's an electron volts, and now we'll get the right answer of 7.25 times 10 to the 16th hertz. All right, let's go back to our atomic scientist, and we'll go to 1896, Henri Becquerel. He's French, so it's probably like Henri Becquerel, but my French is not very good, so we're just going to say Henri. Not Henry, Henri. He discovered natural radiation. He found out that unstable nuclei break apart. They decay, as we call it, and they emit little bits of themselves. And some of them emit tiny bits of positively charged matter. This is the first time radiation was discovered, and so we named them alpha particles, alpha being the first letter of the Greek alphabet. We'll talk more about other discoveries of radiation later on, but this is important because now we have these tiny little bits of positively charged matter that are often smaller than other atoms, and we're going to use these in experiments. By the way, later on it was discovered that really alpha particles are helium nuclei, helium atoms that have been stripped of their electrons, so tiny little bits of matter that have a positive charge. And then we're going to get to 1905, and here's Albert Einstein, and we're just going to go through some of his discoveries here. We already talked about the photoelectric effect. The paper was published in June of 1905, and it turns out in 1921 that's what he actually won the Nobel Prize for. But it turns out he did more in 1905. In July of that year, he published another paper proving the existence of atoms. See, up until 1905, scientists suspected that atoms existed. In 1905, Einstein proved it. And in September, he proposed special theory of relativity. You may have heard of that. And then in November of 1905, he proposed mass energy equivalence. You know, E equals mc squared, the most famous equation in all of physics, right? Even more famous than sigma F equals ma, because people actually know this one. This is all in 1 year, 1905. In 1 year, he published 4 papers changing everything about physics. And he was 26 years old. This has been known as his miracle year. 26 years old. I'm 43. I think, have I done enough? Well, maybe not, but I'm also not Einstein level. But the point is, in 1 year, this guy, who at this point no one had heard of, published these 4 papers and changed everything. This was a huge revolution in physics.